So in 1959, Richard Feynman, the Nobel laureate physicist, said there's plenty of room at the bottom. What he meant is bottom in terms of small particles. He really predicted the nanotechnology of today. I suggest to translate bottom into fundamentals. And I must say, a personal comment, too many researchers at the universities aim to get money, not to get understanding. So I tried to show you that by simple means, it's possible to get also understanding. Some more wisdom. The famous psychologist said there's nothing so practical as a good theory. And not many people believe in it, but I believe. And Einstein had said that everything should be made as simple as possible, but not simple. You have to catch the essence of the phenomenon, but not go beyond it. Okay, now I've been working on surface phenomena, and that's why my examples will be in that field. The question is, why surface is important? Now, suppose that there are no surfaces. So all of us will be soup of molecules, and we will not be able to distinguish one from another. So this is the main thing. And then there are the applications, heterogeneous catalysis, biology, many phenomena in biology are surface phenomena. Of course, industrial processes. Actually, you cannot move one step without encountering surface phenomena in terms of wetting with other processes. I see the movie doesn't work as expected, but this has been a big event in the last 15 or 20 years. Super hydrophobic surfaces. Surfaces that do not wet. You put water on them, it goes away without leaving any stain. This started with the leaf of the lotus flower. So I think 10 years ago there were 58,000 papers on this. And this is going much. So just this example by itself is enough to show how important it is. What you should have seen here is a drop of water jumping. You let it touch the surface, and instead of wetting, it jumps back and jumps back. Okay, this is an anecdote that my research program is actually written in the first book in the Bible. So I don't have any theological meanings here. Just look at it. Genesis, the first book of the Bible. The first thing that God did, according to the Bible, is separate between heaven and earth. So the first thing he did is create an interface. And the second thing is to create light so you can see the interface. And the third thing is liquid fluid interfaces. And the last one was liquid solid interfaces. So here's my program of life research. Okay, now let's get serious. How do we characterize surfaces? In liquid fluid systems, let's say oil and water, we have surface tension or interfacial tension, and this was treated by Gibbs in around 1911. We have solid interfaces. This started in 1805, so it's more than 200 years ago, and we still argue about it. So there's no consensus yet. I'll show you what I think about it later. Okay, so let's start with the simpler system, which is liquid system. By the way, this is my assistant. He asks the questions. I'm supposed to give the answers. Okay. The Gibbs theory. He overlooks many glasses of water or wine or whatever, and you see the two distinct phases here. You see the liquid and you see the air. Okay, how do you see there is a difference here? How can you see it? What is the mechanism by which you see it? Optics, basically. So this reflects light differently than the air. And this looks like a discontinuity. So this was the model by Gibbs. He assumed it to be discontinuous. Let's say if this is the density of the liquid, so the air is close to zero, the liquid has higher density, and there is a discontinuity. However, the real profile of the density with position is something like that. So what Gibbs said, let's invent a dividing surface, an imaginary surface that separates between the water and the gas. But there is one important property of it. If you assume the dividing surface to be here, and this, the red is the connection, because there is no dividing surface. It's just a smooth profile. So if you put it here, you get a certain correction. If you put it there, you get a different correction. So it means that if you can touch the place in the interface, you get different values of surface tension. But this is not true. In all systems that we measure, you get the same value. So something must be missing there. And let's think about what energies have to be. When we talk about energy of a volume of material, it has to be proportional to the volume. And if we double the volume, we double the energy. In the same way, if we talk about surface energy, if the surface is doubled, the energy of the surface must be doubled. So when we talk about two-dimensional systems like Gibbs talked about, the fact that he assumed the dividing surface to be of thickness 0, the interfacial phase for Gibbs was just a plane with no thickness. If you want to extend it to real life, you have to talk about 3 dimensions, and then this is a simple thing. Then we must keep the thickness constant. I'll show you a picture of it. This is a corrected, enhanced model of Gibbs. Here you have the bulk of the liquid, the bulk of the vapor. Here's an interface. When we do the thermodynamic analysis, we have to keep this constant. If it's not constant, then the energy will not be proportional to the area. So this is the only trick that was missing. When we don't get, I hope you're not afraid of integers, but I'm not going to talk about them too much. Show you, say what it means. P infinity is the pressure, the outside pressure, and these are the stress components inside the liquid. So if you do this integral, you should get surface tension. Interestingly, this was developed by other means by statistical mechanics, and we get the same result now if we assume the thickness to be constant. So what happens is that inside the bar, the 3 components are equal. At the interface, these 2 are the same because of symmetry, and this is different. And the difference is the surface tension. Now, let's see what it says. There's a puzzle here that has not been solved. Just publish it like 2 minutes ago. So this is the definition of surface tension. This is the difference between the pressure and the stresses. And we can say, we don't know how to solve the integral. Let's say this is an average. This here is an average of this integral. So order of magnitude we can average. Now let's take a liquid with a medium size surface tension of 50. you see here, this is the atmospheric pressure, this is the pressure inside the liquid, the stress component. So normally you would say the lowest pressure inside the interface would be zero, because we don't think of negative pressures in the liquid. If we say the pressure, average pressure is zero, this means that this is the same as the outside pressure, so it's 10 to the 5 Pascal. If we assume this, we get the interfacial layer to be 500 nanometers. No weight. It was measured to be about 5 to 10 nanometers. So this is certainly wrong. If we assume a priori the thickness to be 5 nanometers, we get 10 to the 7 Pascal, which means it's inside the liquid there is tension of 100 atmospheres. So it's something unbelievable. Nobody understands it yet, but all simulations show the same thing. That inside there is a region where the pressure is tension, not compression, but tension, and tension at the other magnitude of 100 atmospheres. One of the referees to this paper wrote, from time to time we get a paper that shows us that we don't know enough. So this was a big compliment. Okay. Now, what about solids? Here, as I said before, since 1805, we are struggling with it and don't have the solution. So this is the Young equation from 1805. You see, this is the contact element here. According to the Young equation, it's the surface tension of the solid, the interfacial tension between the solid and the liquid, and this is the surface tension of the liquid. Now we're looking for a number. We have a surface, this surface, we have to coat it, to plane it, whatever. We're looking for a number for surface tension. It will tell us this is the characteristic of the surface. Now this equation is not only for rigid, flat, smooth surfaces, but in short, an ideal surface. And the other thing is that we have two unknowns. This is one equation for two unknowns. So the two unknowns is solved by using correlations like originally Falco-Good and then others. So this becomes a system of two equations with two unknowns. But let's see if the surface tension of the solid can be characteristic from its measurable though. We cannot measure it. So this by itself is enough. It doesn't have theoretical basis. This equation is for liquids. It is not independent of roughness. If you take the same solid with different roughnesses, you get a different number. It's not independent of the liquid. We want to put a number on it so it will characterize it, but this number so far doesn't answer any of the requirements. So what can we do? We can be more modest. We can take the Young equation and not to try to make it into components, just take this as one unit, and that's it. So we'll call this sigma star. Once we do that, we have only one unknown, not two unknowns. We don't pretend to know each of them. We just want to know the difference. Okay, what can we do with the difference? We can write it in a different way with epsilon, which we can call invertibility index. And then it turns out to be nice. When epsilon is equal, there is no working at all. The liquid will form a complete sphere. When it's 1, it's completely wet in the surface. When it's half, it's 90 degrees. So it could be a nice way to do it. I'm looking for people who are willing to try, because to say something like that is easy, but to prove it's correct, this is okay. The last thing is absorption. This is really equation for the moon looks like, and with this, I think I'll